So it's very good to know that the estimates of P will converge in the limit to the true value of P, the failure probability, backed by the strong law of large numbers, as long as our samples from the joint distribution of the basic variables are IID. But obviously we cannot sample forever, so we have a finite sample size. So what happens if we stop after a finite number of samples? How uncertain is the estimate? Can we get some sort of confidence interval? And how many samples are enough to achieve a certain accuracy, certain desired accuracy? So for that, we will invoke another very fundamental law, but we'll come to that in a second. So to recap, we have this indicator function I, which evaluates whether failure has occurred or not. It's 1 if failure has occurred, whose probability is P, and it's 0 otherwise. So the mean of I is P, and its variance is P times Q, or P times 1 minus P, because I is a binary or Bernoulli random variable. We have set up the scheme in which we estimate P hat as an expectation. So we generate X from the joint distribution many times, or n times, and then evaluate G every time, see if I is 1 or 0, and then add those i's and divide by n. So we are computing the expectation. Now, because P hat is estimated from a finite sample size of n, then P hat is a random variable. So if P hat is a random variable, we would like to know what its mean is, what its variance is, and so on. And we have seen such derivations before in this course. So the expectation of P hat, expectation being a linear operator, is what you see on your screen, 1 over n, the sum of the individual i's. And because the individual i's are IID, they have the same parameter small p, so the expectation of P hat ends up being P itself. So that's very good. And what would be the variance of P hat if the samples are mutually independent, which is what we have been stressing all this while? Then the variance of the sum is the sum of the variances multiplied by the square of the coefficient. So that gives us P times Q over n. So the variance goes down with the sample size. So that's very good. Now it's time that we introduced the other great theorem, the central limit theorem. So we also saw this earlier in this lecture in part A. To recap, basically if you add a good number of random variables that are not too dependent and that do not have a single very dominant component among them, then that sum would approach the normal distribution regardless of the individual nature of the distributions of the individual random variables. And we had the entire description of the central limit theorem. We are not going to go into that now, but basically this is what happens if the conditions are met. The normalized sum, normalized and centralized sum would approach the standard normal. So that is what we are going to take advantage of, because our samples in estimating failure probability, sample of all the indicator function, their IID, as we have been stressing. So with the backing of central limit theorem now, we can say that the estimated p hat is going to approach a normal distribution with the mean of p and the variance of p times 1 minus p divided by n. So that tells us that we are now ready to give bounds and confidence intervals on this estimated p. And for that, we can simply refer back to the standard normal distribution and say we want to have the 1 minus alpha percent confidence interval on p. So if we have an estimate p hat, then we can find out, say, the 90% and confidence interval, 95% confidence interval, simply by looking at the standard normal deviates. What you see on the screen is such an interval, the area under the normal distribution curve, alpha over 2 on either side, those shaded regions, and if we have p hat, then plus and minus z of 1 minus alpha by 2 times the estimated sigma, which in turn is a function of n, would give us the confidence interval on the estimated failure probability. So continuing with this thought, how many samples would be enough then for a desired accuracy? So we know that the mean of p hat is p and the variance of p hat is pq over n. So provided the samples are IID, of course. There are two things we see here is that because variance goes down as 1 over n, the standard deviation goes down as 1 over square root of n, and that is actually an inefficient convergence, which is true for all such sampling techniques. But if we want to find the estimated COV, the coefficient of variation, sigma over mean, then it turns out to be the square root of 1 minus p over np, or q over np. Now we can invoke the general property that we are estimating failure probabilities, and these failure probabilities are typically very small numbers. So we actually can safely say that the coefficient of variation of the estimate p hat would be almost equal to square root of 1 over np, n being the sample size and p is the true unknown probability that we are trying to estimate. So then this actually gives us an idea of how many samples to try, how many samples to generate. So suppose we want the COV to be 10%. So that tells us that in that case our sample size has to be of the order of 100 over p. So this gives us a kind of initial guess of how many samples to go for if we have an idea about what the failure probability is like, or conversely, if we have estimated a failure probability from a certain sample size and the COV turns out to be too large, then obviously we have to keep sampling until we have reached our own comfort level in terms of the uncertainty involved.